Hey guys, okay, welcome to the second part of this video, which is we're going to talk about speed time graphs. Okay, as you can see here, right now we have got two graphs, one on top of the other. The first one was the original graph, which was a distance time graph. Next one is a speed time graph. Okay, this simulation actually shows a velocity time graph, but we can actually basically just consider that to be a speed time graph in this case over here, because our guy, our main man over here, is just going to move forward. We're not going to have him move backwards. All right. Okay. So let's start off this guy. As you can see, this guy is basically at the about minus 9 meter mark. So that's what we agreed previously. The distance time graph should just be a horizontal straight line. But you see, the speed time graph is also a horizontal straight line. But if you look at the value of the speed time graph is 0. So it makes a lot of sense here because the man here is not moving. So that's why as time moves on, it's not moving. It's basically a flat line with a value of 0. Okay, so that's for the first case, the first scenario of the speed time graph. Okay, going to back to page 28 over here. Page 28 of the speed time graph for a car at rest. You're able to see over here the horizontal straight line with 0 acceleration. So just to highlight this. Okay, let's just look at the second scenario first. Second scenario, the man moving at uniform speed. Okay, so just to recap earlier, if it's moving at constant speed, you actually see a constant slope up. It's not like an increasing slope or a decreasing slope, something like that. So you just basically be a uniform slope, where the slope at the start, in the middle, at the end is all uniform, same gradient. Okay, let's check it out. Okay, so as you can see, start moving him at the same speed. So you can see over here the blue line tells us that speed of the man is actually uniform. So you can see over here, as the speed of the man is uniform, what happens? The velocity, he's actually moving at constant velocity of 3 meters per second. So it's constant all the way until it stops at the end. So immediately when it stops, you can see the line here becomes horizontal, and for the speed time graph it drops all the way immediately to 0 here. You can see. So a horizontal flat line on the speed time graph does not necessarily mean that it's not moving. It means that it's moving at a constant speed. Okay, so just the last time, constant speed, distance time graph, constant slope, but speed time graph is a horizontal flat line that points to the speed. Okay, at the end here, let me just make it a bit longer. So at the end here, as it's not moving, we can also see that the speed time graph is also a horizontal line, but with a speed of 0 here. Okay, so going back to our textbook, page 28, we just covered the first two scenarios for a car at rest, an object at rest, and an object traveling at uniform speed. So you can see both are horizontal lines, whereas one has a value of 0, the other one has a value of 10 or 20, whichever is that particular speed. Okay, so both have 0 acceleration and both graphs have 0 gradient. To draw this arrow just to indicate that. Okay, only difference is that this speed is 0 meters per second, this is 10 meters per second, and both their speeds don't change, which is why both are horizontal lines. Okay, alright, going to the third scenario. Let's see. Third scenario over here, same thing. We got a speed time graph below a distance time graph, and our good man, what's he gonna do next? Let's see. Starts moving a bit slowly, faster and faster and faster, all the way until it bangs into the wall. Okay, let's check it out one more time. Okay, as he moves faster, starts off a bit slow, moving on faster and faster until it bangs into the wall. Okay, let me just show this here. Okay, let's check this out. You can see as speed increases, because for distance time graph, as the gradient increase, speed increase. Okay, but what about the speed? Speed, you can see it actually increases at more or less a constant rate over here. So although the gradient is increasing for a speed time graph, the velocity or the speed if a gradient is increasing for a distance time graph, the gradient is the same for the speed time graph. Can you see the gradient here? Basically the same level of steepness. Okay, over here is a little bit off because it's quite difficult for me to actually control the man in the simulation. The simulation is actually very sensitive. Okay, so our third case here, car traveling uniform acceleration. What do you mean by uniform acceleration? Okay, we basically just mean that every increase in speed per second is actually the same. So you can see over here 0 to 10 is 10 meter per second, 10 to 20 increase of 10, 20 to 30 increase of 10, and so on. So just draw these arrows in, put a plus 10, and do highlight these words, increases by 10 meter per second, and you see a positive constant gradient. Okay, constant gradient because you can see the slope is the same. What do you mean by positive? Positive means it as the time increase, the speed also increase. That's why this is a positive value. Okay, so over here you can see the acceleration is constant. Okay, what's the opposite of this? Okay, opposite of this is let's just look at the and same thing, speed time graph, distance time graph. So what happened to the guy? The guy starts off by moving faster than the previous one. So let's move at it again and go back. Come on. Alright. Okay, see, starts off moving faster, and after that slows down quite a bit. Okay, so slows down, then it stops moving. So you can see it moves very fast, after that it slows down. So in other words, speed time graph, same thing, starts on 5 meter per second, after that it slows down. So this part here is more or less about the constant or the same slope, alright, constant gradient. So looking at a fourth case, uniform deceleration, this part here, we're actually talking about this part here, okay, where the man actually slows down. Okay, so uniform acceleration is basically the opposite of uniform deceleration, sorry about that, is the direct opposite of uniform acceleration. Okay, that means you can see as the time passes, in every second, the speed actually reduces by minus 10 meters per second. So speed decreases, just help me to highlight this, put these arrows in, and you can see it has a negative constant gradient again because the slope is the same, but negative because over here it's negative. As time increase, the gradient actually drops. Okay, so deceleration is constant. So what do we see about the slope of a speed time graph? So just highlight this again. Gradient of a speed time graph gives the acceleration of the object. Okay, so you can see negative gradient means it's decelerating, positive gradient means it's accelerating, zero gradient means it's neither accelerating nor decelerating. It means that the speed is constant. Okay, alright, part E and F. Okay, so if we have a car that's traveling with increasing acceleration, all this means is that the increase in speed per second is not constant and is increasing. For example, from 0 to 1 second increases by 2 meters per second, 1 to 2 increases by 6 meters per second, 2 to 3 increases by 10 meters per second. So you can see there's an increasing trend over here. So increase in speed is increasing. It means that the acceleration is increasing and the graph has a positive and increasing gradient. Can you see the gradient here? It gets steeper and steeper. So the video, I'm going to show you a video later again, of how we actually, what's the meaning of these triangles. These triangles are mainly just to find the gradient. That means you can see for the same amount of increase, same 1 unit of time increase, over here, this is the increase in speed. The same unit of time increase here, you can see the increase in vertical speed is actually longer than this. And the same one, from 4 to 5, you can see the speed increase is much greater than the previous one. So in other words, it is increasing acceleration. Okay, an example will be a boy. If you are playing in time zone, one of those initial D track championships. Okay, this is what's going to happen. Basically, you step your car on the pedal slowly. Okay, so your car will actually basically increase with increasing acceleration. But how many of you actually do that? You probably are doing this, right? When you move, uniform deceleration because you step all the way in, correct? That's right. Okay, so uniform deceleration, non-uniform and decreasing acceleration simply is the opposite of the previous case. That means it starts off, it slows down, or rather it increases by a lot. Then after that, the increase gradually declines. Okay, this is like if you have reached the maximum speed, you actually slow down by releasing the pedal slowly. Okay, so increase in speed is decreasing with time. So you have a positive but decreasing gradient. Alright, that means your acceleration decreases. You can tell it's still acceleration because it's a positive gradient. Okay, for both this and this case, it's still accelerating. But this is increasing acceleration, decreasing acceleration. The only part that is decelerating is for this case over here because it's a negative slope. Alright. Okay, basically, hope this particular example actually shows you a little bit more about the different increases, the different performance of a car. Okay, so over here, as long as I have a constant positive gradient, the green line, it means that the speed is actually increasing uniformly. Over here, the black line, increasing speed is still increasing speed, but increasing speed at a decreasing rate because my gradient is getting less steep. Okay, so please do highlight this part here. Okay, over here that is horizontal, it means it's a uniform speed, both the top and the bottom. The only difference between the top and the bottom is that this is uniform speed, but the top one is at 20 meters per second, whereas the bottom is uniform speed at 0 meters per second. That means it's at rest. Okay, this blue line here is the first sign of it decelerating. So since the gradient is constant, I say that the speed is decreasing uniformly. Okay, we just covered this earlier. And over here again, decelerating, so decreasing speed at decreasing rate because the gradient again is actually decreasing, becoming more and more gentle, less and less steep. Okay. So one final thing I just want to talk about speed time graphs is that in the speed time graphs, in a uniform speed, if let's say I have an object that's traveling at 6 meters per second, we know from primary school, after 14 seconds, the total distance traveled is simply 6 times 10. Oh, sorry. At the end of 10 seconds, the distance traveled is 6 times 10. So if I do 6 times 10, that is basically just finding the height times the breadth, which is the area under this graph here. Okay, do highlight this part here. Okay, distance equals speed times time because speed is constant or no acceleration. Therefore, okay, do put a star here. The distance is the area of the rectangle under the speed time graph. Okay, so just highlight this new point about speed time graphs. This is a very useful information and very important piece of information. Okay, the area under the speed time graph, it tells us the distance. So there are two things. It must be a speed time graph first. After that, we are looking at the area. For example, if I'm looking at what's the distance traveled from in the first 10 seconds. So I just look at the graph, look at the area under it, which is this yellow shaded part. And by calculating the area, I can actually find the distance. That's right. Okay, so this is useful not just especially for graphs that has a non-uniform speed. That means accelerating, decelerating. So, for example, over here, consider this graph. I have an acceleration, constant speed, deceleration. So the total distance traveled in 24 seconds. I just calculate the area x, y, and z. That's about it. Okay. So calculating of total distance. Okay, do highlight this in your textbook. This is on page 33. 33. So over here you see acceleration, deceleration, no acceleration. So write this down also, x, y, and z. So total distance is this, or I can put area of x plus area of triangle x plus area of square y, or rectangle y plus area of triangle z. Okay, so triangle x is just half base times height, half 6 times 36 over here, plus area of rectangle y is base times height again. So be careful not to use 15, it's actually 15 minus 6, so this length here, so that's why I have 15 minus 6 multiplied by the height, which is 36, okay, plus area of z is half base times height again, so half 24 minus 15 times 36, okay, so the rest is basically just math, so that is the total distance. I can actually calculate average speed, and yes, okay, so speed increases uniformly from time equals 0 to 6 seconds. At 6 to 15 seconds, the speed remains constant. At time 15 to 24 seconds, there's a decreasing speed. Okay? So, for this other, we'll just look at one more example over here. Example 2.6. Highlight the word average speed, so we know how to calculate average speed. But in part B over here, when they ask us to describe the motion of the graph from 0 to 10, 10 to 70, and 70 to 90, first thing we need to know is the first part here. Please underline the word graph, positive and constant, because this part here is constant gradient, so therefore it's constant or uniform acceleration. What about this part of the graph from 10 to 70? Okay, 10 to 70, I see a horizontal line, that's why the gradient is 0. So gradient in the speed time graph represents my acceleration, so acceleration is 0. Okay, final part here on the speed time graph, you can see this is the first time it has a negative gradient, not just negative, but the gradient is decreasing. Can you see here? Decreases, starts off with very steep, after that more and more gentle. So I have a decreasing deceleration, thus it's a negative gradient. Okay? So to write this down also at the bottom of page 34, negative gradient, deceleration, decreasing gradient means decreasing deceleration. Okay, so just a recap. Okay, the gradient over at page, what page is this? Page 36, okay? Page 36, gradient of a distance time graph tells us the speed. Gradient of speed time graph tells us the acceleration. These are the various cases, and the distance is the area under speed time graph. Okay, so that's all for this particular video on graphs of motion. Hope you found this video useful and helpful. Alright, have a great day. Bye bye.